Hi everyone, welcome back. I hope you are ready for a long tutorial on nuclei segmentation. This is going to be a mega project or a large project, let me put it that way. And our goal is to perform all the tasks on the left-hand side that you see on the screen. We are going to do a full project where we start from nothing, download data from Kaggle. Obviously, I'm not going to sit and download and stare at the screen. I'll show you the process. And we need to clean up the data because it comes with a lot of directory structures and everything. And the data itself is basically raw images with annotations in multiple formats. Unfortunately, we don't have the format that we need, which is mask or CNN type, right? COCO JSON format and also YOLOv8 format. So we're going to convert our labeled masks into both of those formats. And of course, before doing that, we need to visualize the annotations. So I'll give you code for how to visualize these annotations multiple ways. The one way is on the right-hand side, as you can see, put like these circles. And again, this is by reading the JSON file, right? And of course, one of the goals is to train a Detectron model, train a YOLO model, and then see how everything is working. So this is a lot, so we need to jump in right away. But at the same time, I try not to rush it, so you can actually, to make sure that I'm not overlooking any concept. So you'll get a lot of code with this, at least 4 to 6 different Python files for various tasks. And even though the main task may not be of interest to you, there are certain subtasks like visualizing annotations, little things, right? And the code can be useful for you. So I hope you watch this video and also wait for the next one. And again, you'll be notified if you hit the subscribe button right now. And while you're hitting the subscribe button, look for the thanks button right there if you're feeling extra generous, and go ahead and contribute how much ever you want to. And why I want you to keep an eye for the next one, because we're going to train a model here, and we'll take the trained model, and in the next tutorial, we're going to segment a whole slide image. If that's of interest to you, stick around and let's continue that in the next video. Okay, before wasting any more time, because I think I already talked for 2.5 minutes, let's go ahead and jump into it right away. And here is the Kaggle link. Again, I am going to post that as part of description along with the links to the code. And this is the data set we'll be working with. And this is a tremendous data set if you want to train a generic or generalized, I should say, nuclei segmentation model. And by the way, this tutorial, of course, this is focused on nuclei segmentation, but it can be applied to anything, basically. Very large data set, 2 gigabytes, as you can see, well, relatively large data set. And it's got a whole bunch of stuff. You'll see folders for human organs and mouse organs. And within human organs, these images are collected. These are H&E-stained images, as you can see. And within human organs, you have images from cerebellum and cerebrum, like some of these from brain. They are colon and a whole bunch, kidney, liver. So you have a very good mix of images. This is why I say this can be a great data set to train generalized models. And in addition, you also have mouse. So if you only want to train it on human organ images, then you can just go take a subset of this. But we are going to use the entire thing. And when I scroll down, you'll see the way the data is organized. You see that there is a folder for human bladder, or if you want to call it directory, there's a directory for human bladder. And within that, you have a whole bunch of subdirectories. We don't need a lot of these. We do not need, for example, distance maps. We do not need binary without border and so on, stacked mask, all of these. We only need labeled images. Of course, we need tissue images. These are the raw images. We need labeled masks. I checked labeled masks and labeled mask modify. I want to keep the labeled mask modify. So anyway, I downloaded the whole thing and then I cleaned up. So which is going to be our first step. And if you want to know more about this data set, I will also leave a link to this publication. Of course, that's also as part of, I believe, the Kaggle, they included that. But either way, I'll leave the link to this and you can read more about this data set. So there you go. So that's the plan. And now, before jumping into training our instance models right here, this is on Google Colab. First thing first, I wanted to go through the data handling part. So I downloaded this, and then what? So when I downloaded this, this is the data I got. So within my data, you have human bladder, just like this showed. But I cleaned it up. So when I go to human bladder, there are only 3 directories here: tissue images with all the images of the tissue, as you can see, and label masks modify, which is actually, let's go ahead and have a quick look at, I don't know, bladder number 4. That's fine. You see how these are labeled images. And now let's actually take tissue images and number 4. So this is the corresponding image, corresponding mask. And you can see each object is given a unique value here. That's why they go from dark to bright, because the bottom right is probably the highest value number. I think this pixel value is 123. So each cell, each nuclei, is given a unique pixel value. That's why they look different. Anyway, so this is how the data set is. Now we need to convert this into or a mask or CNN compatible format, which is the COCO style JSON file, a single JSON file that kind of summarizes the annotations. So multiple steps, right? So we need to clean up. I have already cleaned it up because you only see these 3 directories. Otherwise, you see a whole bunch of stuff that I showed you in the background on the Kaggle page. Okay, I also left mask binary without border because I may need it for other tasks. This is just a binary, which is, we may as well look at it. This is just a binary without the border. These are just, instead of pixel values 0, 1, 2, 3, 4, this is background is 0, the foreground is 255. So it's a binary mask. And sometimes this can be useful if you are doing semantic segmentation. But for now, we will completely ignore that. I'm just keeping the whole thing as is. Okay, now I have a few files locally here, Python files, for, just like I said, data cleanup purposes. So remove unwanted data and so on. So let me open my IDE right here. So here is everything that's open, and here, this part basically cleans up. So I am gonna say, hey, just look for tissue images, mask binaries without border, and label mask, and these are the directories to keep. Other than these, delete everything else. This is simple Python code. You can take this and use it for other purposes. You can generate your own if you want. Just type a question in ChatGPT or something. I'm pretty sure it gives you a code that's 90% there, and you edit it and you can get it working within 10 minutes or so. But if you don't want to waste that time, I have my code right here. That I'm going to share with you anyway. So after this task, I downloaded the whole 2 gigabytes, right? So, and then I did step number 1, which means this data got cleaned up. So all the folder structure just remained. You see how I have all human and mouse, everything intact. It's just that within each folder, it doesn't matter whatever I open, I have 3 directories. Okay, now let me close this so we can focus. What is the next step? Next step is, let's zoom in. I should be a bit more prepared, but that's okay. Zooming in is easy. I added a whole bunch of text. Oh, sorry. First thing first, we should do this step first. Oh, God. Okay, my keyboard is underneath and it's unreachable. Okay, there you go. So next step is, right now, what we have is just binary masks or labeled masks, right? We need to convert that into COCO style format. I have actually done a couple of videos in the past, but I don't know if you watched it. So I'm gonna share the code and explain this at a high level right now. So what are we going to do? Get image and mask pairs, right? So if tissue images in the root, so we have to find a way of identifying these images and pairing them with the appropriate masks. And every data set is different. If you are using exactly the same data set, here it is. So you are identifying these images, you're actually getting these image paths, and you're creating an image path list right here. And then what it's returning is image and mask paths, right? So it's actually looking at these tissue images. For example, it says human kidney 04.png. Now, if you go back to labeled masks right there, it also says human kidney 04.tiff, right? So we're taking exactly the same name. And did I take care of tiff right here? Yeah. right there. So you can see .png and .tiff, because what's going on here is the annotations are .tiff and the images are .png. So I just had to tell this program that, hey, go ahead and look at the replace these and look for this extension PNG and TIFF. And I don't know if you understand why these images are in PNG and not the labeled masks in PNG. The simple reason is in one image you may actually have, I don't know, 3,000 annotations, 3,000 nuclei. Then if you just use an 8-bit PNG, then the maximum number of objects you can have is 2 to the power of 8, right? 255. So that's why typically for these type of annotations, you see .tiff right here. Okay, with that explanation, let's go ahead and continue. So now we need to convert those masks to polygons. And what do? We actually find the contours. We use find contours from OpenCV. All it's doing is for each of these objects, it's actually finding these contours. And go ahead and experiment with find. If you don't know what this function does, load one image and apply find contours and change certain settings and see how it's actually drawing a contour or a circle or a polygon around your objects. And once it's done, then we are actually converting that into a polygon. So basically you're getting the coordinates of the polygon that defines this contour. And this is what our annotation is. And we have a main function called process data where your input path, mask paths actually go in. And then we are going to call this mask to polygon function down here. And we are going to create a JSON file very similar to the JSON file structure that that you see in COCO style, which is basically you have images, you have annotations, and you have categories. Annotations is nothing but your polygons right there, and categories is if you have one category, which is what we have in this case. This is nuclei category, and images. Obviously, this is a list of your images, and for each image, like in images, under images, you have an ID associated with the image, file name, height, and width. And all of these we are actually extracting because we know what the file name is. ID, we'll just add an ID. We'll start a counter. Where is it? Image ID equals to 0. We'll add a counter, and then for each image. And within each image, you have an annotation. So we have a counter for that too. Again, this is straightforward Python code, so if you go line by line, it should make sense. But this is exactly what converts your labeled masks into COCO JSON. And I'm also copying the images and placing them into appropriate directories, train directory, validation directory. So if you go here, I am creating let me go back to my root directory. I am saving everything into something called COCO output, which I defined right here, right? And my input data directory is data. So within the COCO output, it actually places them into train and val subdirectories. And within train, I should have all the images for training, and the JSON file for training is also placed here. I did the mistake of calling both JSON files like just COCO annotations. I should have just called it COCO annotations training, COCO annotations val, but it's okay. As long as they're placed along with the images, I think they will be, it's pretty intuitive, right? It's in train. Similarly, I have val right here of all of these annotations. And one other thing I should mention is, where did I put that? Sorry, let me minimize this. One thing, instead of copying all, I actually, I should be a bit more prepared, but let's see. I'm actually basically, in this case, converting only the data, because here we have so much data, and I don't want to waste any time training on the entire thing for now for my tutorial. In real life, that's what you should be doing. But if you look at my COCO output, I only have human bladder data right here. And human cardia and human. So this is basically the human data set, I believe. I don't think I did mouse. Oh, I did. So I've been doing too many things in parallel. So my apologies. That's why I didn't find it here. I thought I had another piece of code where I was like just testing. By the way, in case you're wondering, well, what is this guy talking about? because I have lots of images here, because I have 533 images in this case, with lots of annotations. It's not just 533 images. There is so many annotations in each of these. I actually took a subset, and I was like, while putting together my code, to train Detectron, and then I'm dumping the entire data. I don't want to test on entire data while putting the code together. So please ignore my last couple of minutes. I shouldn't have brought that up, but I was doing that a couple of days ago, so I thought, okay, maybe that's the latest situation. So, okay, now going back to track. Now we have COCO annotations ready. I also want to show you in a single video. I don't want to make another video and make you guys wait 2 more weeks just for YOLO, which is ridiculous. So while we are doing this, let's also train a YOLO version 8 in case you are a YOLO fan. And for that, we need annotations in the text format, which is what the YOLO dataset expects. So the next part is exactly that. Now that we have COCO JSON, let's go ahead and convert the COCO JSON file format into the YOLO format, and a lot of text here that you can read. And also, in addition to the text annotations for YOLO, let's open this. The output looks like this. I have train and valid, and within train, you can see I have images and labels. And I have images. This is no brainer. You know what that means. And when it comes to labels, for each image, you have a corresponding annotations right here as a text file. And the text, if you open it, you see the object number and locations and all that kind of stuff. It's just a different way of presenting annotations to the algorithm, but we need to get our data into that specific format. And in addition to that, we also need to create a YAML file. Like, let me drag the YAML file here, which is nothing but 4 or 5 lines right there, which tells you what the classes names are, how many classes do we have. We only have 1 class in this case, and what is the path for my test, train, and validation. This, of course, we'll modify when we upload this to Colab for our training, but this needs to be created either manually or in an automated way right now as part of this code. So that's part of the text I just added at the bottom. So again, go ahead and go through this if you want how to convert this to YOLO. All we are doing is taking this input and saving those as individual text files for each of the input images. So at the bottom, I also have a create YAML part right here, where it's just dumping this into a .yaml file. That's pretty much it. Nothing fancy over there. So after this, when you execute this code, you'll end up with basically this one. I already showed you what this is. Now, when I created these, initially I was super happy. I'm like, okay, so I got this. Let's go ahead and train. But how the heck do I know that the annotations are written correctly? Is it like, did I mess up? Like, it's always a good idea to view your annotations before you go and waste your time. Well, I should say spend your time if the annotations are correct, or waste your time if the annotations are wrong, right? In terms of training. So let's go ahead and visualize this. So let me close the files that we talked about, and the you may have different perspective in terms of how you would like to, have a look at these annotations. Now, that's why I'm including 2 files. One is where the COCO annotation labels are showed as a circle, so you can see the object, and the other a circle with filled region. So let's start with this one here. Display images with COCO annotations. Again, we are showing 2 by 2, which is basically 4 images at a time in a size of 10 by 10. Now we are reading the images, these random images, and we are applying color. And there is the polygon that actually gets drawn around these annotations. And now we are executing that function down here by calling the annotation. So basically, we are opening the JSON file right here, and then I'm calling the paint function up there. So no need to explain this in detail. Again, this is straightforward Python, no tricky libraries or anything. So nothing to explain here. So let's go ahead and run this and make sure we load a few random images, and there you go. Those are the plots. I hate when that pop-up doesn't go away, but yeah, there you go. I'm super happy. I can see the annotations right here. They're all in random colors, as you can see. And let's do one more time just to make sure everything looks okay. Yeah, the annotations look good, and the images are fine. And as you can see, the images come in different colors and shades in the background. You can choose to normalize. I have done videos in the past where you can kind of apply normalization to these pathology images, so the background, they all look the same. If you want the model not to struggle much, that's a pre-processing step that I definitely recommend doing. Again, I'm not going to do that now, but watch my previous videos on this topic of normalizing H&E stains and separating HE DAB signals and all that stuff. Okay, so now let's, now we have others. So let's load a few more of these COCO labels, but this time I'm actually filling them. Instead of just looking at the polygon, I'm actually filling those polygons with some color and applying some transparency. That's the only difference. It's up to you what you prefer. But let's just load a few of these. Sometimes I like this, but the problem with this is it covers the nuclei, so I'm not sure if there's really a nuclei there or not, but in some, for some data sets, this can be very useful. Okay, enough of that. Let's move on to our YOLO labels, exactly the same task. Basically what we have done earlier. So let's go ahead and load a few random images and random masks, and that looks good, right? This is a classic example where we have 4 random images loaded. All 4 look so different. I mean, these two probably similar, but look at the background right there. Look at this. This is more purplish. This is more pinkish, and this one is more like a marble color right there because we have no nuclei there, and this is more, I guess, between pink and purple. So the backgrounds are very different. So training a generalized model can be a challenge if you have this type of variability. So a good trick is to apply normalization, stain normalization. That is the video. Go ahead and check. If I remember, while uploading the video, I'll try to put this top tag thingy. I forgot what it's called, but please check for that video. Okay, one last thing before jumping on to our collab. Do exactly the same, except now fill it with solid colors. And yeah, again, it loaded 4 different images with all 4 looking kind of different. I mean, these two probably are similar, but this one has different background and so on. Okay, I think I made this point of stain normalization across. Now that we have all of this done, let's jump into Colab and start working on this data. And let's start with our Detectron model, and let's go ahead and connect, and hopefully GPU is available. I have been using it all day yesterday, so I hope Google is not mad at me. And it has a, I had to stop my work a few times because I'm using free version, and I reach certain limit and it's like, okay, you can't use it. And the day after I try and still I can't use it. But I hope we don't run into something like that during this recording. Okay, it's connecting, and it should have connected to my drive because I already connected my drive and I uploaded my data to the drive. And if I go to my drive, Colab Notebooks data, you should see this data set right here, and I have COCO data set, I have YOLO data set, and COCO data set is basically my train, val, test, and then these results and stuff will generate right now, so let's not worry about it. So with that information, let's come down, and I have done a Detectron video in the past, so you know the first step is installing Detectron. And PyYAML, so we can read YAML files, and we are installing Detectron right here. And again, it depends on, okay, I saw this and I thought it's running into some issues. But once it's done with this installing Detectron, let's go ahead and make sure what type of torch version, CUDA version, and the GPU that we have. So you get an idea of the type of resources I'm working with. Okay, where are we? CUDA 11.8. Torch 2.0, Detectron2 is 0.6. So this is the version. And this is, of course, 2023. I'm recording this in October. I don't know when this will be published, but sometime, hopefully not far away from this date. Let's go ahead and import our required libraries. Again, this is Detectron2. And we are going to import model zoo right there. So because we need some model to start with that we are going to kind of fine tune. And default predictor is something, an object that we need to define, and get configuration. Configuration file is something we'll define. Visualizer can be useful obviously for visualization purposes, and metadata catalog, dataset catalog helps us extract information from the data sets that are registered using COCO instances. I don't know why I'm not importing that library. Maybe I'm doing that late. Oh, right there. So we're doing that step right here. So we are registering COCO instances to create this data set, and the data set name is my dataset train and my dataset val. And what does that data set contain? It contains annotations. So the first thing that we provide here is the annotation file, the .json we just created. And the second one is where are the images located. So they are located in train, right? Same thing in val, we have the annotations file. And once we do this, it's going to register all that data. And now we can apply this metadata catalog to get or metadata information. Same thing with the dataset catalog to get the dataset information right here. And we can use this to plot and do all kinds of stuff. And we have 465 images, and we have numerous, probably thousands and thousands of annotations, because each image has on average about maybe 100, 50 to 100 objects. And 133 validation images. And now, again, another sanity check. Let's go ahead and visualize a few of our annotations overlaid onto our images, just to make sure, again, another sanity check. Hey, is everything working fine before we go ahead and start training the model? The more checks, the better it is. This is useless. Lots of objects with a lot of text. Okay, so this tells me that, okay, everything looks good. So now we are all set to train. Now, before training, we need to set our configuration. So we do that by actually defining a config file, get config. Remember, we imported this earlier from Detectron, and we are defining a get config. I'm not sure why I'm importing default trainer. Did I import it up here? Oh, we did default predictor. We did not get default trainer, but we have this get config, as you can see. So let's go back, come back down here. Okay, so there you go. So Detectron2 default trainer. We initiate the config file, and to that we are going to add stuff. So first thing first, where do we want to save our output? Into a folder called Detectron2 models. This is where everything will be dumped. And where do we get, what is the pre-trained weights? Do you want to start from scratch, or do you want to start from pre-trained weights? I am going to start from pre-trained weights, where the model is mask-rcnn, R50fpn 3x YAML file. And where is my training data set coming from? It's my dataset train. In fact, I forgot to add .val. You see, I added .test, but .test, actually, I should have added my dataset. I don't want to change the code right now, but go ahead and under test, go ahead and add my dataset val. And that gives it the validation dataset. And number of workers, let's leave it to 2, and model weights. Right? So this is the model that we are downloading, that we are referring to, but we haven't told it to load pre-trained weights. That's just a model structure with random weights. So the weights, we are going to update the weights of this model by downloading the weights from here. Okay, next. Images per batch. This is the batch size. How many images do you want to process per batch? I put 2 images, and remember, 2 images may mean 500 annotations, right? So be careful in terms of what number, especially when you're working with free resources on Google Colab. Learning rate, I just set it to this. Go ahead and experiment with this. And for demo purposes, I changed it to 1,000. I believe I trained a model with 15,000 or something, or 5,000. We'll see in a second. And yeah, if you want any decay in learning rate, you can go ahead and add that here. And batch size per image, 256. So 512 is default. I'm just adding 256. This is the batch size basically of how many objects or ROIs. So think of this as objects. So 256 is okay. I don't have more than 256 objects per, and I don't want to define more than that. And how many classes do we have? Only 1. Remember, in some frameworks, you probably have to define 2, because one is background and one is object. But in this case, how many ever objects you have, that's all you need. I think that's good. Now we instantiated the trainer by using our default trainer class right there with config as the input. And yeah, so this one is good. Let's go ahead, and it may take a few more seconds because it needs to download this mass Gaussian and weights. But once it's done, we should be all good. Yeah, there you go. Read everything over there. And this is the part where it is going to train. So let's go ahead and run it. I'll stop it because, of course, I have already trained it. And while it's doing, you can actually open the TensorBoard and have a look at it. But let's see. In fact, let's go ahead and run this. Wherever the models are stored, this is where the Detectron, this is where I should have opened this first actually, but it's okay. It's telling me for this 1000 iterations, it's going to take 6 minutes 41 seconds. And this is the loss initially. And let's wait. Now it's 6 minutes 30 seconds. So that's the total estimated time of arrival. So let's go ahead and stop it. And I'm going to stop that. And you can load the TensorBoard if you want. And this should, because I have trained it earlier, this should show me the earlier logs. Let's see. I mean, in one of my previous videos, I was wondering why the TensorBoard wasn't working, and then it was a silly mistake. The log directory, I was pointing at some other random location. You have to point at the right location. So in this case, it stopped right here, but you can open like older ones if you want, and look at the training right here. Okay, so anything else I want to show? Now let's go ahead and close this and come back down. Now that the model is trained, I saved it in Detectron2. So if I go here, drive, my drive, collab notebooks, data, where is my N, right there. And here I added a directory called models. I mean, it creates that because I said go ahead and save it here. And in here we have something called Detectron2 models, and in Detectron2 you can see a whole bunch of stuff right here. The last checkpoint and model 15K. This is something I saved earlier, and right now the last checkpoint is the one I think I didn't even think in 2 epochs or iterations it saved anything, but there is my 15,000 iterations saved right there. Let's go ahead and load that. I mean, this part is basically saving it because by default, the name it gives when it saves the final version is model_final.pth. I tend to do this multiple times, so I don't want to overwrite my 15K. So I saved it as 10K, 15K, whatever. Now let's go ahead and load that 15K file. And here you can actually set a threshold. Like basically, you get a probability for an object being a nuclei or background, right? So that probability, you can actually set it right here. I set the threshold to 0.2. And if you don't train your model for a long time, you may have to drop this threshold down to 0.01 or something. This is not really a probability value. This is not like 20% probability. This is more of a threshold value. So go ahead and define that. Let's start with 0.2 and see where we go. If we see that it's missing a lot of nuclei, we'll change that sensitivity. Think of that as a sensitivity value. Okay, so now that we have this, I also have test images that I haven't registered because when I did this COCO output, I have val trained, but I also have test data. So I am going to register my test annotations, and because I want to test my model on test data that the model never doesn't know that even exists. So I am going to work on this test data. And by the way, the reason you don't see the test folder right here is I have done that later on a different system, and I obviously apparently forgot to copy it to this system locally, but of course I uploaded that to the cloud. Okay, now what are we trying to do? From my test data, we have the test metadata, test data dicts. What I'm doing here is go ahead and get a random sample from my test data dictionary. Get only one sample. You can do multiple images if you want, but in this example, I'm only getting one image at a time so we can focus on it. And then read the image using OpenCV. And how do you predict on that image? Predictor. and you put your IMY predictor. That's exactly what we defined right there, which is the default predictor with this updated configuration file. And this updated configuration file, all it's doing is loading this 15K iterations weights and setting a new threshold. Instead of the old threshold, it updates the threshold if there was any other threshold defined. Okay, so it's applying the predictor onto my image, and then we are just visualizing the image. That's as simple. And I'm using OpenCV, and because this is a Colab notebook, I cannot just do cv2.imshow. There is a function called cv2_imshow. That's exactly what I'm using. This is one of the things we imported earlier. Okay, so with that information, so there you go. That's the image. Oh, that's pretty good result. I'm super happy with this. And you see how I'm displaying nuclei, even though this specific nuclei has a 33%. I'm kind of showing that this nuclei also has 33% of confidence. I'm showing these because I have set my threshold to 0.2. Set the threshold to 0.3, 0.5 or something, you'll see some of these being missing. But I'm super happy with this result. Go ahead and check this on a few. Maybe it fails on the next one. Let's check. I don't know how good this is. Oh, it's actually doing a good job. So I should claim that I know that this model is great, and then move on. But we have a quantitative way of actually doing that, right? So we can apply the above model to filter more objects. I'm not going to run this. I just want to show you. If you want, instead of, even though I set my configuration threshold to be 0.2 right there, you can change your mind and you can say, hey, just show me all the objects with a threshold of 0.4 or something. That's the purpose of this part of the code. So let me move ahead. Now let's check the segmentation metrics, and this COCO evaluator can be very useful to evaluate the function. So now I'm providing this a input data set because we have ground truth for the test data set that I just provided. We can actually check against this ground truth or predictions. So let's do this. I forgot what I got earlier. I think I had, I added notes down here. I did not open this notebook in 2 weeks, so let's be surprised. I did something 2 weeks ago. Everything was working. I'm like, great, ready for my tutorial. And here you go. I'm sitting and I'm like, okay, so why did I write this? Okay, so all it's doing is, as you can see, it's calculating this average precision. It's doing average recall. In case you don't know what those are, you should be, because these are some of the useful metrics when it comes to segmentation. Let's focus on this AP 75, APs, so on. So AP means average precision. AP 50 is average precision calculated by setting a threshold of 0.5. But we know 0.5 is a bit high. 0.2 is what we want, but still 0.5, the average precision of 72 is pretty incredible. That's pretty high. I'm happy with it. But as you keep looking for better and better accuracy or precision, then as you see, only 35% here. And if you look at APS, that is small objects, our score is 32 when you're looking at small objects precision. And if you're looking at medium objects, it is 50. And for large objects, apparently we don't have any large objects. I have to dig into what it thinks medium is, small is, and large objects is. But sorry for that. Look at the documentation of this evaluator, COCO evaluator, to understand what the limit is for that. You see how it says large, medium, and small, but I don't know what it calls large, medium, or small. Okay, now that we know that, now let's say, okay, let's load a random image and then segment it, right? I'm just showing you many ways. I just don't want to say, hey, here is the test data set, something. Now, after this, one of you may leave a message under this video by saying, hey, I just have individual images. Like, how do I register a data set? Or I don't have ground truth. What do I do? For those of you, here it is. I have a brand new image, like something.png. Let's say I think this, I downloaded that. Oh no, this is test. In some cases, I just Google search download from the internet and then try to segment to see how generalized this model is. But this is not one of those examples. This is one of the images that came from the test dataset. All you need to do is apply your predictor onto this new image and then visualize it. That's it. You're done. There's not much to do. That's why I like Detectron. It's doing an amazing job. I'm super happy with this model, actually. It's doing such an incredible job. I'm a big fan of Detectron in general. Okay, so now this part I kind of commented out because this is about processing multiple images in a directory and saving the results as a PNG or or a TIFF file, whatever it is, as a binary or a image or labeled mask. Let's not go there. If you want, you can uncomment and check that yourself. Now let's go and look at the next part, which is segmenting images and saving the object level information. This is exactly why we do most of the time we train these models, right? We want to segment nuclei, and I want to get a average nuclei size distribution, for example, or what is the area, what is the aspect ratios, and whatever metrics you want to get. That's exactly what I'm trying to do here. And first thing first, to do that, I'm going to use region props from scikit-learn, scikit-image-measure, and also label, because we need to convert these images, the output, to a labeled image, and that labeled image acts as an input for this region props. So for each image, and then all the region props output, I'm saving those into a pandas data frame, and then that data gets written into a CSV file. So that's the whole thing going on right here. Let's go ahead and run it, and this may take a while because it's going through every test file and then looking at every object and so on. And also my directory, the test directory, may have some non-image files. That's why I added this valid extensions right here. I believe whenever I see that, yeah, valid extensions, because if you have a JSON file or something else, then the program stops, and that's a pain. So okay, so there you go. Now you have a CSV file. What do you do with the CSV file? Let's go ahead and load the file. Let's say we are done with this, and now we are in the analysis mode. We are done with training a model. We're done with segmenting our data sets or images. And now let's load the CSV file and do some fun plotting. So first thing, we know that we have human and mouse, right? So what if we can just extract the base name like human or mouse and go ahead and plot average nuclei per that base name? That base name, again, in our example, is human or mouse. Or did I do it even further? Yeah, I think I did this even further. So it's not just human or mouse. You can also do that if you want. But in this case, I'm actually looking at, for each of these image types, because we have human bladder, multiple images. We have human cardia, multiple images, right? So for each of these, we have multiple images. I'm just curious to see, is there a relationship, or what can I gain from this? I have no clue. I'm just plotting, and from here you can say that, okay, we see a lot of nuclei in these human tonsil and mouse femur. We have 60 nuclei per image, and so on average. These are average nuclei per image. And the muscle tissue has the fewest nuclei. Again, I don't know what to infer from this, but just plotting the values. Now, average nuclei per unique file name. So this is average area now, not just the... so do some of these nuclei, are they larger area compared to the others? So most of the time, it's not like I see a clear trend. It's just that human liver, the nuclei size is pretty large, and same with mouse liver. So this is where being a biologist definitely helps. I pretend to be one. I am actually not one, right? So I have no answer to the question whether liver actually shows larger nuclei sizes, but based on this data, yes, of course, I'm seeing large nuclei sizes because I see the same trend between both human and mouse, right? So fun stuff that you can do. I'm just showing you quantitative analysis because it never stops with segmentation. It's always some follow-up after that. Okay, now let's look at human versus mouse. Okay, previously we just saw various file types, human versus mouse. And again, go ahead and study how many objects, in the humans we have more, mouse you have kind of less, although there is a significant overlap over there. And let's do one more and actually average area of nuclei by category. So let's look at human versus mouse. Again, human, the nuclei size is on average Not that much, but larger compared to mouse. Okay, so that's a lot, and I think I added some optional topic and already covered in previous tutorial number 330, which is basically saving labeled masks for further processing, so I'm not gonna touch on this. I think, I don't know, I lost track of time, probably 45 minutes to 50 minutes into this entire tutorial. I really want to make sure you have energy, and I have energy to talk, you have energy to listen about this final topic, which is same thing that we have done here with Detectron, but we'll do that with YOLO. And let's go ahead and disconnect. My mouse is getting stuck. Okay, runtime, disconnect and delete the runtime. So it gives me a GPU for this. And I hope, keeping my fingers crossed, it lets me connect. So this part is identical to what we have done earlier, except here we are using YOLO instead of Detectron2, which means the labels that we are going to load are also different. And again, I added a lot of text for you to follow, but let's go ahead and install YOLO, and it is available via Ultralytics package. First thing first, let me edit and clear all outputs and Ultralytics. And then we are going to import our YOLO from Ultralytics and Matplotlib and Pillow because we are working with images. And what model should we be using? So we are going to use YOLO version 8N, and this is the YAML file. So this is a new model, and we are going to populate this model with the weights that come from this. So that's exactly what's going on here. So build a new model from YAML and then transfer the weights from a pre-trained model to that specific model. And once that is done, now we are, this step, I mean, I was getting some error when I was trying to install certain libraries and run certain lines. So because it was Google Colab was having an issue with recognizing UTF-8 encoding. So I just added this part in. I mean, if you don't run this, run some, the other lines when you see some error related to UTF-8 encoding. Obviously you realize that you should be running this. That's why I included this, okay? Because later on, for example, if you're trying to download data that you have already annotated on RoboFlow using Colab, you may run into this issue. So there you go. So that's the line. Okay, let's load YAML file that contains the name of our classes. So remember, we have a YAML file that we created, my drive, Colab notebooks, data, that one. And now we are looking at YOLO dataset and the YAML file here. Let me open the YAML so you can see everything else I left the same, but I added the paths to the test, train, and val. I edited those right here, and that's it. This is our YAML, and from here, once you load it, it should know exactly where to look for your test, train, and val data sets. So number of classes, I'm defining them again instead of typing it myself because it's coming from YAML file. Let's go ahead and define it right there. So number of classes equals to 1. Now we are ready to train a model. So first, let's define a project. And I'm going to call this project results. And when you define a project, it creates a project right there. You see how it's called this results. And you can define a subdirectory. And within the results, within this project, it creates whatever names. If you see here, I have 20 epochs, I have 50 epochs. So you just give a name right there. It just creates that over there. So all your results are nicely organized. So let's just leave this to 3 epochs for now because that is what I plan on doing. I have already trained it apparently for 50 epochs. Again, I haven't looked at this file in a couple of weeks, but it's not like I don't know what I'm doing. It's just that I forgot what I have done 2 weeks ago. but everything is intuitive. So the name is 3 epochs right there. And what are we going to train? We are going to train our model using what? My data is coming from this YAML file. Go look at the YAML. You know what my train is, test is, and validation is. And my project is this project. So it creates this results. And the name of this training is the name, which is 3 epochs. And how many epochs? Obviously 3. And if you want, you can set patience to some number, which is basically how long should the model train after reaching the best training. And just to ensure that that is indeed the best training. Patience 0 basically means it just goes to, if you set 3000 epochs, it trains for 3000 epochs. Yeah, batch 4, load 4 images, and my image size is 512. So let's go ahead and start the training process, and we can stop. The YOLO is a bit slow, the training process, compared to the Detectron2 mask or CNN approach. But let's go ahead and starting the tensor board. I mean, it's telling us go ahead and start the tensor board with this log directory. That's what I'm doing down here. But once it starts training, I'll stop and move on to the next steps. Yeah, it just started training, as you can see, and there you go. So of course, mask or CNN or any of these type of object, you have a box, bounding box loss, and you have the segmentation loss, right? So, and the classification loss, obviously. Don't forget about this. We only have one object, so there is nothing like classification. It's just either nuclei or not a nuclei, but these are all the different losses in case you wonder. So as you can see, it's about a minute per epoch. So let's go ahead and stop this. I have already done the training, so that's fine. Where are we? Okay, right there. Let's not worry about the tensor board. And get down here, and yeah, it actually saves. That's one thing I should show. So let's look at the 50 epochs, because once the training is done, it actually saves like the results for each of these batch numbers at each of these batches, and also there is a results.png. So what is in there? So that's exactly what we're going to look here. So for that, let's go ahead and get this image, and we define this image results.png. You can use pyplot if you want to plot that PNG, but yeah, this is how the training actually went. I could have actually gone at least 20 to 30 more epochs, because you see how it is still going up. This is still coming down the loss. So we are not really there. This is not really the perfect training. I think at least 20 to 30 epochs should have done this. And what is this? This is the results from the last batch right there. And it looks okay, I guess. I mean, there's not much going on in those images, but we'll test all of that in a second. Now, every time it actually, within this, you should have, within the models, oh, that's Detectron, sorry, YOLO. There should be 2 models. If I can find them. Where are they? 50, where is, there you go, weights. So there should be 2 models. One is the best one is the last one. So it's up to you what you want to load. So here, this is basically listing that, okay, we have best and the last. I am loading the last, but you can also try the best. The last may be the best, who knows? So now, from this point on, forget training. Now we are in the inference part. So I have a trained model, I'm loading it. So I'm loading it by using this YOLO method and by pointing it to the right model right there. And now I'm reading a new image, just some random image. Okay, so let's read a new image and then apply the model. So it's basically your model.predict and your new image, whatever the input image is and what the confidence is. And let's go ahead and run it. And let's look at the results. So basically, the results right here, you can see that it's actually saying, okay, it found nuclei, 35 of them in this specific image, and it's giving you all kinds of other information. So let's go ahead and plot. I'm using just pyplot to look at that specific image. There you go. That is pretty good result, as you can see, right? And very good probabilities. If you see some of the nuclei are being missed, obviously you know what to do, change the confidence, but this is pretty good result, even with 50 epochs. Same story, segmenting and analyzing multiple images. So let's go ahead and do the same CSV plot. this part is very similar to what we just did. That's why I wanted to do this in one video, because I don't want to go through the whole thing again in next video by dividing this video into two. But this is exactly the same, almost, the code wise. And I added some print statements because it was doing some issue. I was running into some issue, I guess. Or is this default? No, I did not mute the output, but it's always good to see what's going on here. So it's 23 nuclei in that image, 17 nuclei, if that's a word, 32, 89 nuclei. So it's got all these nuclei, and now we just need to load that CSV file. We did this last time and do exactly the same plot. You see, the numbers are plus or minus. I mean, you can go and verify these numbers. That's not the exercise I'm interested in right now. I think in the new one, we see a lot more of this last class. You see how we have 50 nuclei here? In this case, it's detecting a lot more. It'd be interesting to load only the mouse thymus images and see which one is giving you more accurate results. But everything else, the trend looks exactly the same. If you normalize that, if you take that back, you see very similar trend and everything. Okay, more plots. Again, I included all of this thinking that I would do this in 2 videos, but it doesn't warrant 2 videos. So this information, this is more tight actually spread here, and average area of nuclei by category, almost identical, I hope, right there. So 800 plus something, this is about 700. So what does this say? Oh, a lot more. So again, this is the time when you get in and investigate whether YOLO is over segmenting these nuclei or what's going on, because this is average area of nuclei, right? So obviously it's picking up a lot more pixels, a lot more pixels here compared to Detectron2. Or is Detectron2 missing a lot of large nuclei? That is an exercise. I'll leave it to you, but based on some random images, both of these are actually doing an equally good job. So I'm not sure where that would have actually come from. Because I see these. If at all, I think this one is exaggerating the nuclei size. I should have printed the original image side by side and the overlay image. Then you can study whether something is being over segmented. If that's the case, we should probably go back and change the confidence to like 0.7 or something and see if that helps. Okay, I keep extending this. I'm pretty sure this is much longer than 1 hour. Thank you very much for sticking all the way to the end, and please remember to tune in next time, which I believe is in a couple of weeks, where I'll take this segmented model and segment whole slide images. So if that's of interest, I'll see you in the next tutorial. Thank you very much.